4 ways to represent a function. We will represent a function verbally, numerically, visually, and algebraically. So first, let's look at this verbally. The dependency statement. So the dependent variable is completely determined by some independent variable. Let me give an example. Determine the function describing the dependency statement for the surface area S of a cube in terms of the length of each of its edges, X. So the area of each side. So I have here a cube, and the length of each side is X. So let's try to find the area of this cube, the surface area of the cube. So let's first look at the area of the top. Well, if I look at the top here, this is just a rectangle. As a matter of fact, it's a square. And so the area of the top is, well, the area of a rectangle is length times width. So in this case, it's, well, X, this length X here, and this length X here. So X times X is X squared. So the area of the top is X squared. Let's look at the area of the bottom. So here, this bottom here as well, again, is a square. So it's X times X. And so the area of the bottom is X squared. Let's look at the area of each of the sides. Well, each of these sides here, the front facing side, the back facing side, each of these 2 sides, the right and left sides, have an area of X squared. And there are 4 of them. And so I have here the area of each side is X squared. There's a total of 1, the top, bottom, and there's 4 sides. So there are 6 total sides. The area of each of those 6 sides is X squared. And so the surface area of my box is 6X squared. We will usually use functional notation to denote the surface area of the box in terms of the length of its side. X here is called the independent variable. S here is called the dependent variable. Let's look at another concept of a function, the function machine. And so we have some input. We can think of this. So we have some input, and then we have some function machine here that somehow does something and it gives an output. We can think of the function machine as, well, a vending machine. And so you select some candy bar, let's say your favorite candy bar, and your vending machine then goes and grabs your candy bar and outputs your candy bar. Now, this choice that you press the button, you put in your coin and you press the button, that is called an input. This is the independent variable. We'll usually denote the independent variable by X. So you select your candy bar. Your function machine, your rule, then churns out and gives you an output. You want that this output is unique. It'll be called the dependent variable, usually denoted by Y. So if you input that you want a candy bar, and sometimes your vending machine gives you a candy bar, other times it gives you a lump of coal, coal, you'll not be happy. So you want that this, if you give an input, once you've specified an input, you want a unique output. You don't want that sometimes, when you press your candy, you press that you want this candy bar, that sometimes it gives you coal and sometimes it gives you candy bar, you will not be happy. And so you want a unique output. So once you have specified your input, your output is then specified. Let me look at the idea of a function numerically. So let's first consider order pairs. A relation R is a set of ordered pairs. A relation is called a function if the set of ordered pairs have distinct first coordinates. Let X and Y be sets, then the domain of F is a subset, and let the domain of F be a subset of this set X. Then we will denote by F colon X being mapped into Y, that this will denote a function from X into Y if F is a subset of the Cartesian product of X and Y, of the sets X and Y, and if for every X in the domain of F, there exists a Y in the set capital Y, such that the ordered pair XY is in the set F, which is a subset of this Cartesian product of the set capital X Cartesian product with the set capital Y. In other words, and we want that that if you're given an input, you have a unique output. So we have that if the ordered pair X comma Y sub 1 is in F, and if the ordered pair X comma Y2 is in F, then Y1 is equal to Y2. Meaning that if you specify the same input X, then you always have the same output Y. Notation. We call the set X the corange of F. We call the set Y the codomain of F. F of some set A is a set of all F of X such that X is in A. It's a set of all images under the mapping F for any member in the set A. The range of F is just F of capital X, the corange of F. Here, the notation Y equal F of X denotes the image of X under the mapping F. And so this denotes, so Y equaling F of X denotes that the ordered pair X comma Y is in the set F. So usually we don't write this notation. We usually write this notation. So let me give some examples. Determine if G is a function. So G is given as a set of ordered pairs. if x is 1, g is 5. If x is 2, g is 1. If x is 3, g is 2. If x is 2, g is 3. If x is 5, g is 0. If x is 6, g is 7. Note that if x is 1, if x is 2, g is 1. So 2 is mapped to 1 by g. But we also have here that if x is 2, g is 3. So g maps 2 to 3 also. So sometimes when you think you're going to get a candy bar, sometimes you get a candy bar, but sometimes you get a lump of coal. So therefore, g is not a function. And so we see that if we have this set of ordered pairs, then if x's here are the same, then these y's must be the same. Otherwise, and so then this is not a function. So if you have two x's here, two first coordinates, then no, this is not a function. But I've got to be a little bit more careful than that. So let's determine if f is a function. So when x is 1, f is 2. When x is 3, f is 4. When x is 1, f is 2. When x is 5, f is 4. So let's determine if f is a function. So I have to sort of modify what I said because I have to be a little bit more careful. So if I look here, well, all the x's are not the same. I have a 1 here and a 1 here. Okay, so that looks bad, but it's not really as bad as it looks. Because if x is 1, f is 2. Here, if x is 1, f is also 2. So what we've done is we've actually repeated these ordered pairs. So when you write a set, you should never repeat the same elements. And so because we repeated the same elements, you're falsely led to think that maybe, this is not a function. But remember that if you have a set, you must eliminate all duplicates. So 1, 2 is the same. The ordered pair 1, 2 is the same as the ordered pair 1, 2. Let's get rid of this ordered pair. So now, if I get rid of that ordered pair, I see that the x's aren't repeated, 1, 3, 5. So yes, f is a function. So I have to sort of modify my rule that I sort of said. If after eliminating all duplicates, if all the x's are different, then this is a function. If the x's are repeated, then it's not a function. So if after you've eliminated all duplicates, you find that the first coordinates for two different ordered pairs are the same, then no, this is not a function. Next, let's look at how do you find these using a rule. And so I have here that x is mapped to y according to this rule f. A rule f mapping x, the set x, into the set y is a function if for every x in the set capital X, there corresponds a unique value y in capital Y called the image of x under the mapping f, and is denoted by y equal f of x. So if I have some sets here, capital X and capital Y, and I have some rule here, F. And I have that for every X in the domain of F, there corresponds a unique Y in the range of F. So the sets X, capital X, is called the corange of F, and the set capital Y is called the codomain of F. The set of all images of members X of the domain of F under the mapping F is called the range of F. So the set of all images is called the range of F. The set which has an image, the set of all X's which have an image is called the domain of F. Now, many times in many books, people will assume that the corange, the set X, is the same as the domain of F. The only reason for having these codomains and coranges is because we're lazy. We don't want to actually determine what the domain and range are for a function. So sometimes we'll just say, let f of x equal 1 over x. Let f of x map the reals to the reals, where f of x is equal to 1 over x. Well, in a strict sense, that's not a function because, well, R is not the domain of your function, and neither is the other R on the right-hand side, the range of your function. So some instructors, some books don't consider that to be a function until you specify exactly what the domain is and write the function from your domain to your range. But even though they say they do that, they actually don't do it. So we're all lazy and we all sort of don't figure out our domains and ranges. We just say a function goes from this set to that set, and we don't really want to have to figure out what the domain and ranges are. And so even though people may say that, may not specify these coranges and codomains in other books, they actually do it without specifying it. But the reason that they don't do that is because in some situations, especially when dealing with inverse functions, then they do have to assume that the corange is the same as your domain. And I will actually use that also. So I will actually also assume that when I'm talking about inverse functions, that my domain is the same as my corange. But in general, we don't have to worry about inverse functions until Math 262. So in this course, usually these are not the same thing. Usually domains and coranges and ranges and codomains are not the same. Again, that's just so that I can be lazy and not have to figure out domains and ranges. Unless they tell me to. So unless they say, really figure out what the domains and ranges are. So let's do an example. So a nice visual example. Determine if f is a function. And so I have here set capital X, consists of the numbers 1, 2, and 3. The set capital Y consists of the objects, the letters A, B, and C. So f here is some rule mapping 1 to A, 2 to A, 2 to C, and 3 to C. And now it says, well, is this rule a function? The answer is no. Because, well, you're specifying that you want a candy bar. Sometimes you get a candy bar. Other times you get a lump of coal. So you're not very happy. And so because of that, that means that this is not a function. So if you look here at the 2, it sort of peels off and goes in 2 different directions. That's bad. And so this is not a function because of this little problem here near 2. And so no, f is not a function. We can still figure out domains and ranges, etc. So the domain and the codomains and coranges. Let's figure out the domain of my function. So the domain of f here is this. Well, let's see. What are all these? Well, the thing, anything that emanates from, that f emanates from, is in my domain. So 1, 2, and 3 have lines that go out from it. And so, yes, the domain of my function is 1, 2, 3. Let's figure out the range of my function. So what are these mapped to? And so if I look here, A is mapped from something. And so it has an arrow going to it. C is also mapped from something. And so A and C are in my range. But B here is not in the range because it's not, nothing is mapped to B. And so the range of my function is just AC. The codomain of my function, well, let's see, what's the codomain? Well, it's all this stuff. The codomain is A, B, and C. So the codomain of my function is there. So the codomain of my function is A, B, C. The corange, well, let's figure out the corange. Well, the corange is, well, 1, 2, 3. So the corange of my function is 1, 2, 3, the same as my domain. Functional notation. And so functional notation is extremely useful. It is also an area of vast confusion to calculus students. You must be sure that you know functional notation and that you're very comfortable with it. The major areas of places where students get points taken off is the fact that they are confused with this concept. So suppose I want to do the following problem. I have here, oops, y equal, let me just check. Oh, that's wrong. Suppose I have here y equal x squared. And suppose I want to answer the following questions. Determine the value of y when x is 2. Well, that's easy. And so the value of y when x is 2 is, well, replace x here by 2. So y is equal to 2 squared. 2 squared is 4. So y is 4. Suppose I then ask you the next question. Determine the value of y when x is 3. And so I have here y is equal to 3 squared. Oh, 3 squared is 9. Now let's try to do this. And using functional notation. It turns out that using functional notation, the same question is actually easier to ask because the notation sort of helps us with the question. So let f of x equal x squared, rather than writing y equal x squared. Oh, big deal. Instead of saying y, I'll call it f. So the name, instead of the name being a y, I'll call it an f. And in parentheses, I'll tell you what this independent variable is. The independent variable is x. So f of x is x squared. I want to determine f at 2, meaning determine the value of y when x is 2. So this is obviously much shorter to actually write. And so wherever I see an x, I replace x here by 2. And so f of 2 is 2 squared, which is 4. Same exact thing I did here. Now, well, let's figure out f of 3. So wherever I see an x here, I replace x by 3. 3 squared is 9, just like what we got before. This notation is read, and you probably heard me say it, f of 3. F evaluated at 3. F evaluated when x is 3. I'll usually just say f of 3. So I'll just usually say the of. So f of 3. But sometimes I'll say f evaluated at 3 or f evaluated when x equals 3. The vertical line test. This is a visual way of determining if a curve in the plane represents a graph of a function. So suppose we have some curve in the plane, and let's draw this relative to some coordinate axis. So I have some coordinate axis. Here's the x, y axis. And this curve relative to those coordinate axes. Now, if I can find a vertical line that intersects this curve in more than one location, say this curve here intersects in 2 places, say this curve, this line here intersects the curve in 3 places. If I can find at least one line, at least one vertical line that intersects the curve at more than one place. So I found a line here, a vertical line that intersects. So this curve here intersects some vertical line at more than one point. Then this curve does not pass the vertical line test. If this curve does not pass the vertical line test, then this is not the graph of a function. If instead every vertical line intersects the curve in at most one location. So it could intersect this curve. So again, this is a curve relative to some coordinate system. If I take this vertical line, I see it intersects at one place. This vertical line intersects at another point. This vertical line intersects at another point. This vertical line doesn't intersect anywhere. But you notice that every vertical line intersects the curve in at most one point. So either 0 or 1, but not 2, 3, just 0 or 1 places. If every vertical line intersects this curve in at most one point, then this passes the vertical line test. If the curve passes the vertical line test, then this is the graph of a function. So there exists some function, let's call it f, such that the graph of y equaling f of x is this curve. Please note one level of confusion that students have in this course is when they graph functions, they'll have functions that, well, will not pass a vertical line test. If a function, remember, if a curve doesn't pass a vertical line test, it is not a function. So if I'm telling you to graph a function, it must always pass a vertical line test. Students, when they first try to graph complicated rational functions, they have a tendency, an unfortunate tendency, to draw things that do not pass the vertical line test. And so we know automatically that that is, whatever you've drawn is incorrect, because if you're graphing a function, it must pass a vertical line test. If it doesn't pass a vertical line test, you're wrong. It's not the graph of function. You have done something incorrectly. So please remember this, especially when looking at trying to draw rational functions. For some reason, this sort of concept, this basic fact that everyone knows, and they think, yeah, I know it, all of a sudden, everyone just sort of forgets it. When we graph vertical line, when we graph rational functions. And I'm not sure why, because we always emphasize this, but it for some reason doesn't sort of stick. Okay, I'll have to tell this another 50 times. We do rational functions. So hopefully people will remember that you know, a function must pass a vertical line test. Okay, so graphs of function, the curves representing graphs of functions must pass a vertical line test. So let me give you some properties of inequalities. If, well, so transitivity. This is true if both of these inequalities are the same. I'm choosing to do this where I've written a greater than, but this could be greater than or equal to, or less than or equal to, or not equal. It could be any of the inequality symbols. I just chose greater than. So if A is greater than B, and if B is greater than C, then A is greater than C. There's transitivity. If Albert is taller than Betty, and Betty is taller than Carol, then Albert is taller than Betty. No, C, Carol. I can't remember the names of what I made these letters. Okay, so if Albert is taller than Betty and Betty is taller than Carol, then Albert is taller than Carol. And again, you could write this as less than. If A is less than B and B is less than C, then A is less than C. Similarly, for greater than equal to, less than or equal to. Oh. But that's not true. But it's not true for not equal. A not equal B and B not equal C doesn't imply that A is not equal to C. That's not a true statement. Okay, so it only is for the greater than, or equal to, less than, or equal to. Those inequality symbols are transitive. Next, we have the additive property of inequality. So if A is greater than B, again, could be less than, or equal to, etc. If A is greater than B, then A plus C is greater than B plus C. So if you add the same quantity to both sides of your inequality, the inequality does not change. So if, I call them Albert and Betty, if Albert is taller than, oh, this could be A is an Ann. Let's make them all female. If Ann is taller than Betty, then Ann on a chair is taller than Betty on the same chair. Next, A greater than B and A positive and C positive, then AC is greater than BC. And so if you multiply both sides of an inequality by the same positive constant, then your inequality remains the same. So A could be, let's say, less than B. If A is less than B, then AC would be less than BC. If C, of course, is positive, greater than 0. Next, if you multiply both sides of your inequality by a negative number, things switch. So if A is greater than B, and if C is less than 0, then AC is less than BC. So if you multiply both sides of an inequality by a negative constant, then the inequality switches. So notice it goes from pointing to the right to pointing to the left. Let me give you some properties of absolute value. And so, assume here that B is greater than 0. So I can write these easily. Oh, I see. I didn't write the degenerate parts. So I'm assuming here that B is greater than 0, just so that I don't need to write all my degenerate sort of absolute value inequalities, which you go over in intermediate, elementary, and intermediate algebra. So let me just do the ones that we really just need in calculus. And so assume B here is greater than 0. If the absolute value of A is less than B, this is the same as saying that A is less than B and negative A is less than B, because the absolute value is just either equal to, the absolute value of A is equal to A or to negative A. And so multiplying both sides of your inequality by negative 1, I have that A here is greater than negative B and A is less than B, which you can write in this abbreviated notation, where you sort of join these all up together. And you've written this as, well, A is between B and negative B. This is sometimes called a three-part inequality. And so A in absolute value less than B is the same as A is between negative A and negative B and positive B. If the absolute value of A is greater than B, then A is greater than B, or negative A is greater than B, which is the same as A is greater than B, or A is less than negative B. So unfortunately, we don't have a nice three-part inequality that represents this in standard sort of notation. So we have to write it as a in symbols rather than as a three-part inequality. Next, the absolute value of A equaling B is the same as A equaling B or A equaling negative B. Next, the triangle inequality. So this is something that's going to be very important. If you don't know the triangle inequality, memorize it. Write it down. And even if you do know it, write it down several times, ingrain it in your brain, because we're going to be using the triangle inequality hundreds of times in this course. And so a triangle inequality says the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. The reverse or inverse triangle inequality says that the absolute value of the difference of the absolute values of A and the absolute value of B is less than or equal to the absolute value of A minus B. And so rewriting this inequality, we can write it this way. This is also, so this is probably not nearly as familiar to you guys as a regular triangle inequality. So I imagine most people have seen this, whereas I imagine few, if any, have seen it written this way, have seen the triangle inequality written this way. We'll also be using this, and we'll be using this week. So in the next like 2 or 3 days, we're going to start to use this several times. So you have to be familiar with this also, that the absolute value of the difference of the absolute values of A and B is less than or equal to the absolute value of the difference of A and B. So absolute value of absolute value A minus absolute value B less than or equal to absolute value A minus B. Ingrain that in your head. Next, interval notation. So, finite open intervals. This is sort of the notation I'm going to be using. And so this open parentheses will denote the fact that it's open. So parentheses A comma B in parentheses. It's a set of all x's such that x is between A and B, and they don't include either A or B. This is the set, well, of everything between A and B, though I'm assuming here, by the way, that A is less than B. So make the assumption here when I'm writing this, my assumption is that A is less than B here. So the open interval from A to B is just all numbers between A and B, but we don't include A, nor do we include B. The infinite open intervals. The open interval from negative infinity to A is just a set of all numbers that are less than A and not equal to A. The open interval from A to infinity is, well, the set of all numbers that are greater than A. By the way, note that when you write your inequalities in standard form, meaning that your x here is on the left side of your inequality, that this arrow here is in the same direction as this arrow. This arrow here is the same direction as this arrow. The finite closed intervals. So the closed interval from A to B, the set of all x's between A and B, including both A and B. So it's a set of all x's between A, it's a set of all numbers between A and B, including both A and B. So that's a finite closed interval. The infinite closed intervals. The interval from negative infinity to A. We do not include negative infinity, but we do include A. So it's a set of all numbers that are less than or equal to A. Everything to the left of A, including A. The closed interval from A to infinity. So we include A, but we do not include infinity. We never include plus or minus infinity if we're dealing with real numbers. There's something called the extended real number line, but for real numbers, we never include infinity or negative infinity. This is just a set of all x's that are greater than or equal to A. So it's everything to the right of A, including A. The half open, half closed intervals. The interval from A to B, including A but not B. And so the fact that we're including A, we put a square bracket. The fact that we're not including B, we put an open parentheses. It's a set of all x's between A and B, where we include A but not B. There's an equal sign for A, but not for B. So I include all numbers between A and B. I include A, but I do not include B. Similarly, we can have the half open, half closed interval from A to B. I will not include A, but I will include B. Set of all x's between A and B, where I do not include A, but I do include B. So it's everything between A and B, not including A, but including B. Lastly, we have the intervals that are both closed and open. Since they're both closed and open, we call them clopen. So we just sort of combine the two words into one word. So the clopen intervals. And so a clopen interval is an interval that's both closed and open. So the empty set. Well, you can't really draw it, but the empty set, nothing. And so the empty set is both closed and open. And, well, the real line. So everything. So nothing and everything. Those are the two clopen intervals. So the real number line, so negative to infinity. The real number line, so it's just everything. Note, some people use the following notation. Rather than having a parentheses, they use square brackets. If the square bracket is in the normal direction, meaning it's the one that includes your inclusion in the interval, then that's the closed one. If it goes in the outside direction, so it doesn't include what's in the interval, then that's the open interval. Then this denotes the open. So this would say, well, it does not include A, but it does include B. Whereas this says, well, look, I don't include A, nor do I include B. So it's the open and open. Even though I like this notation, I'm going to use parentheses. So rather than always use closed bracket, and depending on the direction, they'll tell me if I'm open or closed. I'm going to use the brackets for saying that it's closed and the parentheses to saying that it's open. What side of the interval is open or closed? Because I think most people are used to this notation more than this notation. Next, a review of lines. The slope of a line through 2 points. So suppose that I have the point x1, y1 with coordinates x1, y1, and other points with coordinates x2, y2. And suppose that x1 is not equal to x2. Then the slope of the line passing through these 2 points has a slope of y2 minus y1 over x2 minus x1. Next, the point slope form for the equation of a line. If x1, y1 is a point on the line, and m is the slope of the line, then the equation of my line in point slope form is y minus y1 equal m times x minus x1. Since I have a slope here in the formula, this only works for lines that have slopes. And so I'm not able to put vertical lines into this form. So this only works for non-vertical lines. The slope-intercept form. And so the slope-intercept form for the equation of a line is y equal mx plus b. M here is the slope of your line, and b here is the y-coordinate of the y-intercept. Since this formula here involves the slope of a line, then, well, the line must have a slope. So again, this is not going to be, you cannot write a vertical line in slope-intercept form. So I'm assuming here that this is a non-vertical line. So I can only write non-vertical lines in slope-intercept form. If line L1 is parallel to line L2, well, then this is true if and only if their slopes are equal. If M1 equals M2. Now, when I write, let's make this assumption. When I write M1 equal M2, this says that if M1 exists, then it's equal to, then M2 exists, and M1 is equal to M2. But if M1 doesn't exist, then neither does M2. So if you make that assumption, then this is an if and only if. So M1 is equal to M2 if and only if L1 is parallel to L2. So if you have two vertical lines, meaning their slopes don't exist, then they are parallel. So that takes into consideration that. Next, L1, line L1 is perpendicular to the line L2 if and only if, well, the product of their slopes is equal to -1. Here, you have to assume that 0 times well, when I said they don't exist, I really mean that a vertical line has a slope of infinity. So infinity equals infinity. Here, I have to make the assumption that 0 times infinity is -1. Then this is always true. Then you don't have to specify that vertical line, that these are non-vertical and non-horizontal lines. So two lines are perpendicular if and only if the product of slopes is -1. If and only if, well, let's divide each of these sides of each of these this equation by M1. So if the slope of one line, M2, is equal to the slope of the negative reciprocal slope of the other line, a -1 over M1. So two lines are perpendicular if and only if the slope of one is equal to the negative reciprocal of the other slope. Now, here we make the assumption that if we're taking 1 over infinity, that's 0, and 1 over 0 is infinity. Then this makes more sense. So, and a -1 over 0 is infinity. So we have here that the M2 is equal to -M1 if and only if L1 is perpendicular to L2. And now that works with that little caveat that I gave you for any line, including horizontal and vertical lines. and lastly, again, sorry, symmetry. So let me give you some symmetry. Oh, and we're going to do this symmetry for functions, which means that we'll only have two symmetries to look at rather than, well, seeing if it's symmetric about the x-axis. Obviously, if we're talking about a function is never symmetric about an x-axis. So suppose that we have a function that's symmetric. We have a curve that's symmetric with respect to the y-axis. So a curve being symmetric about the y-axis, well, suppose that curve here satisfies the vertical line test. So suppose that the curve is symmetric about the y-axis and satisfies the vertical line test. So it is the graph of a function. If a function is symmetric with respect to the y-axis, then we say that it's an even function. And, well, if it's symmetric about the y-axis, then that must mean that the ordered pair negative x, y is equal to xy, meaning that f, using functional notation, that f of negative x is equal to f of x. So if f of negative x is equal to f of x, then we say that f is a even function, and we know that the graph of an even function is symmetric with respect to the y-axis. Next, suppose I have a curve in the plane that passes the vertical line test and is symmetric with respect to the origin. Then negative x, the ordered pair negative x, negative y, is equal to the ordered pair x, y, meaning that f of negative x is equal to negative f of x for this function that we get from the vertical line test. And so we call this an odd function. So if f of negative x is equal to negative f of x, then f is an odd function. It is symmetric with respect to the origin. Please note that if f is a power function, and let's say with natural number exponents, then if that exponent is an even number, then the function will be an even function. If that natural number exponent is an odd function, is an odd number, then the function will be an odd function. And so that's why we call these even odd functions. It's because if you look at the power functions and you look at their exponents, well, an even exponent gives you an even function, an odd exponent gives you an odd function. So it turns out that it's actually quite easy when looking at polynomials even to figure out if it's even rational functions that have so if you look at rational functions, it's pretty easy to figure out if they're even or odd functions just by looking at their exponents. Next, and lastly, I guess, let's look at an increasing function, decreasing function and constant function on an interval. So we say that f is an increasing function on the interval I, open interval I, if whenever x1 is less than x2 in the interval, open interval I, we have that f of x1 is less than f of x2. If this happens, then we say that f is an increasing function. As you look at it, as you look at your function, the graph of your function, and you proceed from left to right, if you notice that your y values are getting bigger and bigger, then we say that that's an increasing function. We say that f is a decreasing function on the interval I, on the open interval I, if x1 being less than x2 on the open interval I implies that f of x1 is greater than f of x2. So we have that if we proceed from left to right and we look at our function, then our y value, as I proceed from left to right, my y values will be getting smaller and smaller if my function is a decreasing function. So whenever looking at any sort of notation, terminology involving graphs, proceed from left to right. So always proceed from left to right, the same way that we read English. We proceed from left to right. You read a graph from left to right. If you do that, then our terminology makes sense. So read a graph the same way you read English, then the terminology makes sense. Okay, so again, just to reiterate, if f is some rule mapping x to y, where x is a member of the set capital X and y is a member of the set capital Y, then f maps the set capital X to the set capital Y is a function if for every x in the domain of f, there exists a unique y value in the range of f that is mapped from x to y by this rule f. So x here is called the corange of f. Y here is called the codomain of f. This red is the domain of f. It's a set of all x's for which f makes sense. And this red here is the range of f. It's the image of x, capital X, under the mapping f. The set of all y, such that y equal f of x for x being in the set capital X. Okay, so let me do some examples. I'm switching to another computer. Okay. On page 21, problems 27 through 30. Evaluate the difference quotient for the given. Simplify your answer. So problem number 29. F of x is equal to 1 over x. And my difference quotient is f of x minus f of a over x minus a. Okay, good. This gives us some practice in functional notation. So let me look at the difference quotient. Oops. the difference quotient, f of x minus f of a over x minus a. I will assume, of course, that both x and a are in the domain of f, meaning x is not 0, a is not 0. So this is equal to f of x. Well, f of x is just 1 over x minus f of a. Well, f of a is 1 over a. Wherever I see an x in this formula for f, I replace x by a. And well, x minus a is still x minus a. So let me try to simplify this. Uh-oh. Okay, good. Oops. Sorry. It's having problems with its recognizing the, there it is. Okay, so change this to red. Let me multiply and divide both sides of my equation by, well, let's try to find a common denominator. I want to get rid of the fraction. I want to get rid of the fraction in the numerator. So let me multiply and divide by the least common denominator, which is xa. Okay. So let me do that. Let me multiply and divide by xa. So let me, let me move this down 1. So I have a little bit more room. Okay, so let's multiply inside the parentheses. So this is equal to, well, the x's cancel, so I just get a. The a's cancel, so I just get x. Over, well, x minus a times xa. I want to cancel the x minus a and the a minus x. So let me do this. Let me just put the xa on front. So I'll rewrite my denominator as, let's do ax. I like to go in alphabetical order. As ax times x minus a. Now the numerator, well, that's, well, maybe I'll just rewrite it. I could divide, cancel these out, if they were both x minus a's. So let me change the order. Instead of writing it as a minus x, let's write it as minus x plus a. And now let me factor out from the numerator. Let me factor out the -1. So I'll factor out a minus. If I change all the signs, if I factor out a negative, then I have to change all the signs inside the parentheses. But now that I've done that, I notice that the x minus a's are the same. So I can just cancel them. So this is equal to a -1 over ax. And that's your answer. Now, of course, I should say here, I'm assuming that x is not equal to 0, and a is not equal to 0. So I'm going to make that assumption. If you don't, then you could possibly, well, then you'll be divided by 0. So if you don't, and you don't really want to divide by 0, that's not good. Okay, so let's state that assumption. Oh, there it is. Okay. Okay, so let me do the next problem. Problem number 36. In problems 31 through 37, find the domain of the function f of u equaling u plus 1 over 1 plus 1 over u plus 1. So let's try to find what's called a natural domain. So the natural domain is the largest possible domain. So when we define a function, we must specify not only the rule, but the domain. But the unfortunate thing is that we only define the rule. So we just have a rule here, and we are not saying what the domain is. So we have to sort of make an assumption that the domain, the natural domain, is the largest possible domain, which gives us a real valued function. So the natural domain is the largest domain. So it's the largest possible domain. Possible domain. To give real outputs. So we want a real valued function. So the largest possible real valued function. So it's a domain, it's the largest possible domain for a real valued function. Okay, so, well, for a real valued function, there are really only two things, at least at this moment, that are really bad. One, you don't want to divide by 0. 2, you don't want to take square roots, even roots, of negative numbers. Well, there are no roots. So really, I only have to be concerned with dividing by 0. So I don't want my denominator to equal 0. Actually, this should say not equal, but I'll say equal to 0 and then change it to not equal at the end. So I don't want 1 plus 1 over u plus 1 to equal 0. Neither do I want, so that's one denominator, this denominator here. But this is also a fraction. So I want this denominator to also not be 0. Subtracting 1 from both sides of this equation, I get u equal negative 1. Next, I want to, oh, that's so slow. I want to get rid of the denominator in my very first function here. So let me multiply both sides of my equation by u plus 1. So 1 times u plus 1 is u plus 1. The u plus 1's cancel, so I just get plus 1. And u plus 1 times 0 is just 0. So this is equal to 0. So I have here that u plus 2 equals 0. Subtracting 2 from both sides of my equation, I get u equal -2. So the domain of my function is just the union of the open intervals, -∞ to -2, -2 to -1, -1 to infinity. So it is everything except for plus or minus, except for -2 and -1. So another way of writing this is a set of all real numbers except for the singletons -2 and -1. Or another way of writing this, and this is really sort of sloppy notation, but I actually write it domains this way, usually, as the domain is just the set of all x's not equal to -2, -1. So this notation stands for that, sort of a sloppy notation that we all use. And hopefully, oh, this is actually a u, right? So where u is not equal to, there, where u is not equal to -2 or -1. Okay, let's do another example. In problems 73 through 78, determine whether f is even, odd, or neither. If you have a graphing calculator, use it to check your answer visually. So problem number 76. F of x is equal to x times the absolute value of x. So first, let's check symmetry. And so let's check symmetry. For either seeing if a function is even or odd, you always have to look at f of -x. So let's look at f of -x. Wherever you see an x, I'll replace x by -x. The absolute value of -x is just x. Is just the same as the absolute value of x. And so x times the absolute value of x is f of x. So this is equal to minus f of x. Since f of -x equal minus f of x, we have that f here is an odd function. Since f is an odd function, that means that f is symmetric with respect to the origin. And so I have here that f is symmetric. With respect to the origin. So let me try to graph this. And so the graph of this, well, if I look at the right-hand side of the portion where x is greater than 0, this just looks like the graph of negative x squared. Okay, and so I'll draw x squared, but I'm going to draw it so it's below the the x-axis. Okay. So xy. Okay. Sorry. It's taking a little while to do that. There you go. So let's draw the graph of x squared. So it looks like a parabola, but in this case, the parabola is below the x-axis. Oh, wait. I was looking at this. That's not the original function. Sorry, this is the original function. Okay, so I made a mistake in my statement. And so if x is greater than 0, then this just looks like a graph of y equal x squared. So it looks like a parabola. Now, if x is less than 0, well, actually, I don't really care. It's an odd function. So symmetric with respect to the origin. So I'm just going to flip this over. So the graph looks like, well, a parabola. And then I sort of twisted the parabola to make this other side. So here's my parabola on the right-hand side. And then I twist it to draw your parabola on your left-hand side. So it almost looks like, but it's not. The graph, it reminds you, but not that it's the same as, it reminds you almost like the graph of y equal x cubed. But it's, of course, not the graph of y equal x cubed, but it's somewhat similar to that graph.